Hi, welcome. We're going to be looking at the notes from chapter 14. So I'll share my screen. All right. So in this chapter is about descriptive measures in regression and correlation. Okay, so we'll get to what those words mean. We're going to start just looking at two variables, just like the book and the weight of the books and the number of the pages of the books. And sometimes variables you think might be related, pairs of variables for a given unit. So I took one book and I looked at the weight of that book and the number of pages in that book. So I paired the X and the Y for a given book were like connected by the fact that that data came from a single unit. All right, so here are some variables that might be related. We might see the height and weight for basketball players on the WSU men's basketball team to be related. Maybe, but that would be what we would want to find out in our statistical analysis. So I've looked at all of us old faculty members here at WSU, and you asked us to report the number of hours we exercised and our cholesterol level. We might find that that's related. We might not, but it might be interesting at least to look at. So there are different kinds of relationships between variables, and kind of want to just lay out what the different possibilities. So sometimes two variables might not be related at all. And we could see that as a possibility if we looked at our ages and the last digit of our social security number. We might not find any kind of relationship there, because you might think that social security number last digit is almost like a random number, which would probably be what it is. But until I look at the data, I never open my map. Here's another pair of variables that have a relationship: the volume of ice cream sales and the number of cases of Lyme disease. So what we see is, as the volume of ice cream increases, it is likely that the number of cases of Lyme disease would also increase. Now, it isn't that ice cream is causing Lyme disease, so we can all, not worry about that, of course. But what is going on? Well, what's going on is the hotter it gets, the more those little ticks grow and are ready to sort of cause Lyme disease upon their hosts, if they get you, right? Also, the hotter it gets, the more we want to eat ice cream because it cools us down. So these two variables, volume of ice cream sales in a given month or in a given week, say, and the number of Lyme disease cases are related, but they're related by this variable that's hiding in the background called temperature, right? And here are two variables that you actually can think of as one causing an effect on another. So in the Lyme disease and ice cream, we did not have a causal effect. One did not cause the other, but we're talking about the number of hours worked on a homework assignment and the grade on the assignment. Okay, so you could really interpret this as work more hours, get a higher grade. And so that's the third kind of relationship that we possibly can have. I just want to go through some possible, some terminology. We use response variable to be the Y variable, the variable that we're trying to explain. Other ways of other terms here: response, dependent, and Y variable. The explanatory variable is the variable we're using to explain. So in the case of the books, we were using the number of pages to explain the weight of the book. Okay, so the explanatory variable is also called a predictor variable or an independent variable or an X variable. And I have some pairs here: numbers of hours worked and total wages earned. Now, sometimes if you get paid per hour, then these might be an exact relationship, right? If whatever the number of hours you've worked times your hourly rate equals the total amount of wages earned. Sometimes if maybe you get tips in your job, then the number, your total wages earned might not be exactly related to the number of hours you work. But we certainly hope that if we need more money, we ask for more hours, we work more hours and we get more money. Okay. So there could be either like an exact relationship or more of a statistical relationship between the variables here. So the age of a car and the number of miles on the car. Again, the older cars tend to have more miles, but it's not an exact relationship. So you might find some variability, and that's where we come in, right? We're all about the variability. Gallons of gas at a single pump. So if there's a pump that you go to and somebody buys 10 gallons of gas, then they have to pay one price. And if you go and you buy 11 gallons of gas, then you're going to pay a little, like, you know exactly how much more you're going to pay. So those are related, really algebraically, right? So exactly, there's an exact relationship, not a statistical relationship. And here we have the volume of water in a beaker and the weight of the water in the beaker. That's an exact relationship. Age of a child and the number of words in their vocabulary. There's a tendency for children to gain words as they get older, but every child is different. So there's some adjustments, or there's like some general variability in this relationship. And height of parents and height of their offspring, right? So the taller parents tend to have taller kids and the shorter parents tend to have shorter kids. But, it's not exact, because if you have a sibling that has the same mother and father, you might not be exactly the same height as your sibling. Okay, so the idea here is that these variables can be related. They can be related directly. There's an idea of the lurking variable. So this is like the ice cream and Lyme disease. So two variables are both affected by a third variable that had not been included in the study, right? So we call that a lurking variable. All right. So I just want to take a moment here and look at the idea of a straight line. These examples are really for you to work on your own. If you need some more support on them, we can certainly let me know and I will point you into the direction. But I'm hoping that this is prerequisite material. And I'm going to bring this over to the whiteboard. Okay, so I just transitioned the problem over to the whiteboard. I just put up the X values. I want to show you, make sure everybody can find the Y values. So if X is -4, then we're going to substitute into this equation 4X minus 4. So we have then when X equals -4, we have Y is equal to 4 plus 2 times -4. 4 minus 8, Y equals -4. All right, so we got -4. I know that was in the notes. I just wanted to go through the calculation with you. And let's go ahead and maybe we'll choose a couple more points, calculate those values, and then we'll put them on the whiteboard and connect the dots. Okay, so let's look at, say, X equals 0. So then Y is equal to 4 plus 2 times, so plugging into the equation, 2 times 0. 2 times 0 is 0. And so Y is going to be 4. And then let's go ahead and take this one down here. If X is equal to 4, Y is equal to 4 plus 2 times 4. Y is equal to 4 plus 8. So Y is equal to 12. Okay. So we're going to make a line. We're going to we're going to plot the points and then connect the points with this lovely yardstick. Okay. So the first point that we want to plot is -4. X is -4 and Y is -4. So maybe somewhere around here. We all know I'm not very good at, we already determined that I'm certainly not as good as a software program at getting dots in the right places, but we will continue to try. X equals 0 and Y equals 4. So another dot goes here. And this other one has X equals 4 and Y equals 12. And gee, I could have planned a better axis, but let's go ahead and extend the axis to get up to 12 or close to 6, 7, 8, 9, 10, 11, 12. Okay. So when X equals 4, Y equals 12. So there's a point here, a point here, and a point there. Taking the yardstick. I had to say, never had the advantage of actually having the yardstick when we were on campus, because you can see I'm a little off here, right? Because my scale was off, but let's take it in. So we're going to just connect the line. We'll just go that far, guys. All right. So this is how you graph a line. In this line, we see that as we move to the right, the line increases. And that's because the slope, this line was Y equals 4 plus 2X. And the slope is positive, which means as we move to the right, the line goes up. Okay, so let's go ahead and back to the notes. All right, and you can play around here. You can try, if you'd like, to put in some points, and you would expect this line to be negative. So have a negative slope. So we would the line has a negative slope. So then as you move to the right, you expect this line to come down like that. All right. So we also want to look at the y-intercepts, right? So the y-intercept, we'll just take a moment back over at the whiteboard. See if we can look at the y-intercept over there. Okay, so the y-intercept is the place where the line crosses the y-axis. And we see that the y-intercept is that coefficient, the number in the equation that is not being multiplied by the x. That's the y-intercept. And we see then that that's why this line crosses here. And yeah, that's the y-intercept. So we're going to look at the notes. We're going to read off some y-intercepts and slopes. So over here we have a y-intercept of 2 and a slope of -3. And this is the form that we're going to use for the linear equation in statistics. It's b0 plus b1x, where b0 is our y-intercept and b1 is our slope. Okay, rather than your mx plus b, where m was the slope. Okay, so it's just parameterized differently. And there's a good reason, because in statistics, we expand this to have b0, b1, b2, b3, but we're not going to be doing that in this class, but still it sets you up to understand the notation as you move into perhaps another research methods class. So in this equation here, we went through these, the ones we just looked at above. So the value B naught is called the y-intercept. It is where the line intersects the y-axis. It shows what the value of y is when x equals 0. B1 is called the slope. The slope measures how steep the line is. It determines how much the y value will change when the x value increases by 1 unit. We saw that in the weight of the book example. When we increase the books by 1, the number of pages by 1, and the unit was hundreds of pages, the model predicted that the weight of the book would increase by the value of the slope. I believe it was, it's in the other video, but I think it was 6.5. Okay, so the slope does have this specific interpretation. It determines how much the y will change when the x value increases by 1 unit. It measures how steep the line is. It determines how much the y value will change when x increases by 1 unit. All right, we note that a positive slope is when you move to the right and the line increases, and a negative slope is when you move to the left and the line decreases. So just to kind of jump in and give us one example of a negative slope, go to the whiteboard and quickly y equals 2 minus 4x. We'll look at that guy. Okay, so I'm just going to graph this line. We see that B naught is equal to 2. It's the value that's not being multiplied by the x. That's the y-intercept. And the slope is called B1. It's the value, including the sign, of the number that's being multiplied by the x. So we can graph this line 2 different ways. Actually, it's probably more, but for the purpose of what we're going to do, I'm going to go ahead and find the y-intercept, so I know the y-intercept is the value of the line, the value the line takes on when x is 0, and so that's, write that again. That little box is confusing me. So it's y equals 2 minus 4 times 0, right? And that's 2. So our first point on this line that we're looking at is it's 2. It's 2. So here, x equals 0, y equals 2. And I could take another point. Why don't I take 2, and so I'm going to plug that in, and I have 2 minus 4 times 2, and that's 2 minus 8. So when x equals 2, y is minus 6. So when x equals 2, y is minus 6. And we see here that the line, when I graph it, has this negative slope on it. So that as we move to the right, the line actually goes down. Yeah, okay. And that's what it looks like to have a negative slope. Okay. And so finally, I just want to show you how word problems kind of come together into this, what we call a linear equation or a linear model. This might be something you're familiar with from algebra, so just take a couple of examples here. So a rental car costs $15 a day plus $2 per mile. So in this case, we're going to look at the cost of the car to be y and the number of miles to be X. So Y is the rental cost. And X is equal to the number of miles. And we notice that even before we drive a single mile, we still have to pay $15 for that car, okay? And that's what makes it the y-intercept, okay? So when X equals 0, the cost of, when I've not driven any miles, then the cost of the car is 15. So B naught is 15. And now for every additional mile I drive, I have to pay another $2, okay? And so then 2 becomes the slope. And really it's from that interpretation of the y-intercept being the value of the model when X equals 0, and the slope being that how much more do you have to pay for one more unit of X, right? So those are the interpretations we initially discussed here. In statistics, we'll stick with those. So this is our model, and we have another one here. Let's go to the second problem. If it takes you 10 minutes to stretch and 9 minutes to run each mile, how long does it take you to complete a workout that consists of stretching and running X miles? So if we let Y equal the number of minutes, it's always good to write this stuff down, what your variables are. And X equals the number of miles. And then we see that Y is equal to, even before you get on the road, you got 10 minutes of stretching, okay? And then for every additional mile, for every mile, it takes you 9 minutes. So it's going to be 9X. All right. So that's it for this video. We'll see you in the next video where we're actually going to be working a little more in detail, bringing together the regression equation, some of those ideas around the weight of the book and the number of pages. And we'll put that in formula form. So I'll see you in the next video.